Hello everyone. The title of this video is Identifying End Behavior of Polynomial Functions. So in this video, the examples I'm going to do are taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 5.2, called Power Functions and Polynomial Functions. And I'm under the heading Identifying End Behavior of Polynomial Functions. Alright, so each example I'm going to do is either going to be one of the examples from the reading or one of the try it problems from the reading or one of the exercises at the end of the section related to this particular objective. Alright, so the first one I want to do is try it problem number 4. Alright, but before I get to that, I want to refresh your memory. In a couple videos ago in this same section, I talked about the end behavior of power functions. And I wrote this page out, and I've got it here. The end behavior, of power functions. Remember, a power function looked like this. Y equals, or f of x equals, some number k times x to some number p, right? But we're only going to be focusing on, powers that are whole numbers, right? 1, 2, 3, 4, 5, 6, and so on. So no fraction powers, no negative powers, no decimal powers, right? Just positive whole numbers here. Now, we saw that in that previous video, right? If p was even, right? If this had an even power, x squared, x to the 4th, x to the 6th, x to the 8th, and so on, and the lead coefficient was positive, then the end behavior was, the graph went up on both ends. Now, a way to describe that was, as x goes to infinity, so to the right, or even as x goes to negative infinity, meaning go to the left, f of x, right, the output, goes to positive infinity, right, with all these little arrows and stuff, but you see it's going up on both ends. Now, if the power was even and the coefficient was negative, you just flip that over. The graph would go down on both ends. Right, as x approached positive infinity or negative infinity, to the right or to the left, the value of the function is going to negative infinity. Right, the outputs are going down forever on both ends. Alright, so that was if you had an even power on your power function. If the power was odd, right, if it was x to the 1st, x to the 3rd, x to the 5th, x to the 7th, and so on, and the lead coefficient was positive, then the graph would go down to the left, up to the right. Another way to state that would be as x goes to infinity, right, to the right, f of x, the output, would go up, right, would go to positive infinity. As x goes to negative infinity, right, to the left, as you move left, the value of the function f is going to negative infinity, right, going down. The outputs are going down, decreasing. And then if the lead coefficient is negative, right, but you still have an odd power, it just flips that over. So it's going up to the left, down to the right. So down to the right means, as x goes to infinity, f of x goes to negative infinity. Right, as you go to the right, the outputs are going down. And up to the left means as x goes to negative infinity, f of x goes to infinity. Right, as you go left, outputs go up. So if you have this in mind, if you remember this from that end behavior of power functions video, and you also know from the previous video how to identify the leading term, right, and leading coefficient and degree of a polynomial function. If you remember all that stuff, this is going to be real easy. All right. And I'll put that note up here. I'm going to put this note up right here. The end behavior, what happens to the far right and far left of the function. The end behavior of a polynomial function is exactly the same as the end behavior of its leading term. Is exactly the same as the end behavior of y equals the leading term. So if you can identify the leading term of a polynomial, and you remember how the end behavior of power functions goes, right, this page here, and you should have no problem stating the end behavior of any polynomial function. Alright, so let's take a look at try it problem number 4 from the text. Scrolling down, you got some reading to do here. There's example 6. Here's try it number 4. So they're saying describe the end behavior and determine a possible degree of the polynomial function. Alright, so I'll draw a rough sketch of this. Alright. So their drawing here is, it looks like the highest point is at 1, 3, like that. And it has x-intercepts at -1 and +3, it looks like, and it's like this. It's almost like a parabola, but it's a little flatter at the top than a parabola would be, and then kind of going down like that. It's not totally flat, just kind of flat, but look at this, right? So the end behavior is described with that arrow notation. Right, and I've done this in previous videos, right, on end behavior. But if you're talking about the right end behavior, you're saying what happens as x goes to infinity. Right, this is the right end. And what happens is, the value of the function goes to -infinity, right? If you're talking about x-axis, y-axis, it's going down, and if you go down on the y-axis, that's going to -infinity. And I think they called this function f. Now they just said it's a function, so I'll just say y approaches -infinity, right? Or f of x, or whatever, right? Whatever you want to call the function. But let's say the y values are going down. And then if you look at the left end behavior, what happens as x goes to -infinity? As you move left on the x-axis, see the function's going down again. Y is going to -infinity once again. So there's the end behavior. That's one thing they asked us to do. And then they asked us to put up, what's a possible degree for this polynomial. Meaning, remember, the degree was the power on the leading term. And if you recall my page a second ago, this page here, if the function's graph is going down on both ends like this, just like this graph here, then the power has to be even. So the possible degree, it could be a degree 2, could be a degree 4, could be a degree 6, 8, and so on, right? Just some even degree. And that's all I'm going to say on that one, right? Now, like I said, because it's a little flatter near the vertex than a normal parabola, I would say it's not degree 2 just because of that flatness. I'd say it was probably a degree 4 polynomial, but all we're pointing out here is that it would have to have an even degree. That is all. All right. Now we'll talk more about finding the that we'll be given actual not graphs later. We'll be given actual like equations for functions, and asked to identify the leading term, leading degree, leading coefficient, and degree. And we'll get to that in a minute. Okay, the next example I would like to do is the next try it problem. All right, try it number 5. All right, so let's take a look at that in the text. So example 7, here's try it number 5. All right, so this time instead of giving a graph, now I can show you a graph. I'll go to that desmos.com website, a free online graphing calculator. I'll show you that in a second, but here we're given the function, and it is a polynomial function. I've stated this as well before. The product of polynomials is also a polynomial. So you have polynomial times polynomial times polynomial times polynomial. Right. So this is also going to be a polynomial. So we're asked to express the function as a polynomial in general form. Remember that general form was, you write the polynomial as a sum of power functions with whole number powers, with the highest powered term first, and then, in decreasing order, and determine the leading term, degree, and then the end behavior, right? If you know what the leading term is and the leading coefficient and the degree is, you can state the end behavior. All right, so I'm going to write this function out. And we have f of x equals 0.2 times the quantity x minus 2 times x plus 1 times x minus 5 and we're asked to write this out in general form. And I'll refresh your memory. I know I said it out loud a second ago, but the general form for a polynomial function was y equals a sub n times x to the nth plus a sub n minus 1 times x to the n minus 1, all the way down to some constant term, a sub 0. But as I said earlier, it's the sum of a bunch of power functions where all the powers are whole numbers, right? There's no negative powers, no fraction powers, and so on. All right, so I need to multiply this out. Remember, you can only do 2 at a time here. And it really doesn't matter what order, right? There's the commutative property, associative property for real numbers. So I can multiply these two first. Sorry, so I'll do that. Let's bring this over here. So we have f of x equals 0.2 times, and then x minus 2 times x plus 1 would be x squared, and then you have plus x minus 2x, so it'd be minus x, and then minus 2. And then you still have this times x minus 5. And now I'll multiply these two factors, x squared minus x minus 2 times x minus 5, and see what we get. Now remember how to multiply polynomials, I'm hoping. You just I'm going to take these two terms, let's distribute the x, and then distribute the negative 5 to the x squared minus x minus 2, and then we'll combine like terms. So if I distribute the x, alright, that'll be, I'll do this off to the side, it'll be x cubed minus x squared minus 2x, alright. Now I'm done with the x, now I'll distribute the negative 5, you have minus 5x squared plus 5x, and then plus 10, and then we'll combine like terms, so we get 0.2, and then the product of these two polynomials is x cubed minus 6x squared plus 3x, and then plus 10. Alright, and then finally, to get it in that general form, we're distributing the 0.2. So we have f of x equals 0.2 times x cubed minus, and then this is 12, but divided by 10, minus 1.2 times x squared plus 0.6 times x to the first, and then 2, right, plus 2. Right. So here we go. Right, that was the first part. They want that this is in general form down here, right? The polynomial is written as a sum of power functions with whole number powers. Every single term is, again, a number times a variable to a power, whole number power. And it's in descending order by power, right? Highest power to lowest power. So we have the leading term. Right? The leading term is this 0.2 times x cubed. The leading coefficient is just the numerical factor of that leading term, 0.2. And notice this is a positive leading coefficient. And then the degree, remember the degree is just the power on the variable in that leading term. This is a degree 3 polynomial, which is an odd power. So if you go back to my end behavior page for power functions, this works out the same way for these polynomials. I have an odd power in the leading term and a negative lead coefficient. So the graph of this function is going to be, when you talk about end behavior, going to be going up to the left and down to the right. So putting this together, we can talk about the end behavior of this function. It'll look like this. And it's going to be going up to the left and down to the right, when you go to the far left and far right. Now what happens in between, I don't know exactly. We'll talk more about that stuff in future videos. And if I wish to describe the end behavior, I would say, as x goes to infinity, right, so as you go to the right, the value of the function f of x is going to negative infinity. Right? It's going down, a little arrow notation. That's the right end behavior, right? And the left end behavior is as x goes to negative infinity, the value of the function is going up. So to positive infinity. So as x goes to negative infinity, f of x, the value of the function is going to positive infinity, right? And there's the end behavior described in symbols. And again, they wanted us to state all this stuff too, right? And write it in general form, right? So a lot of stuff that they asked for us here. All right, so what I'm going to do right now is show you a picture of this. So let's see that this is actually the end behavior of this polynomial function. So I'm back here. I'm going to go to that Desmos website, right, desmos.com, free online graphing calculator, and I'm going to enter the function in both ways. Right, so y equals, we were given this, 0.2 times the quantity x minus 2 times the quantity x plus 1 times the quantity x minus 5. And look at the end behavior. Oh, I had a positive lead coefficient, didn't I? I even wrote the word positive. Wow, you're probably yelling at me. My bad. I wrote the word positive, didn't I? So going back here, we had odd degree, right? Odd power, and a positive lead coefficient. So it should, should be going down to the left and up to the right. So that changes these. So to the right it goes to positive infinity, and to the left the output goes to negative infinity. So I'm just changing the signs there. So my apologies on that one. So I'm glad I went to Desmos check my answer. You should always be checking your solutions anyway. And I noticed that I made a mistake, right? I said positive lead coefficient. That's this case here. Okay. And again, let's take a look. Right, so you see the end behavior matches that, positive lead coefficient and an odd degree down to the left, right? Down to the left, up to the right. And let me just verify that when I multiplied it all out, it's the same thing. So let me punch in y equals, we had 0.2 times x cubed minus 1.2 times x squared plus 0.6 times x, and then plus 2. And yes, it is. It's exactly the same, right on top of the other one. So that means, I did a good job multiplying it out at least. I didn't make any errors there. Okay. All right. But one more time, right? The end behavior of a polynomial is exactly the same. It will be exactly the same as the end behavior of the leading term. And the reason for that is because x is getting huge. It's getting big positive or big negative. When you go to the far right and far left, x is getting gigantic. And when you raise numbers to higher powers, big numbers to big powers, they're a lot bigger than all these numbers with lower powers. So like you could say that the leading term dominates the rest of the terms when it comes to having, giant inputs, x going to infinity or negative infinity. Okay, great. All right, so for the next examples, so we're now just, again, given a function and asked to determine the end behavior of these functions. These the functions we're given are polynomial functions. And all we need to do to determine the end behavior is know what the leading term is, right? So really you just have to identify that leading term. Identify the leading term. And if you know the leading term, you'll be able to very easily, unless you make a little error in word, I spoke the word positive but said the word negative later, and it threw me off in the last example. So be careful. I use I like using my calculator, the Desmos, to check me. But you should be able to identify what the end behavior is once you know the leading term, right? So this one's nice, right? This first one, f of x equals 3x squared plus x minus 2. It's already in that general form, right? Highest power to lowest power. So we can very easily identify, the leading term, right? The leading term is this 3x squared term, right? So the leading coefficient is positive, and I'll try to remember that I actually said the word positive this time. It's positive 3. And the degree of this polynomial is 2, right? This is a quadratic polynomial, which is an even power for the lead term. Right? So again, I'll pull up that page. Positive lead coefficient, even degree, even power. So even power, positive, right? I said positive, lead coefficient. The graph should be going up on both ends. Right? And this should be the graph of a parabola. This is actually a quadratic function. You know how the graph of a quadratic function looks like a parabola, right? But the function will be doing this, go up to the left and go up to the right, if I'm talking about end behavior. All right, so as x goes to infinity, as you go to the right, the function value is also going up, right? F of x is going to infinity as well. And then the left end, as x goes to negative infinity, we're going up. The value of the function is going to infinity again. Right? As x goes to negative infinity, the left end, f of x is still going to infinity. Right? And there's the end behavior. Now you can draw a picture or do. They also ask you for symbols. Do it in symbols as well in a lot of these. Great. And let's just verify this by looking at a graph, right? I'll enter this in Desmos, or you can graph it by hand, right? You should know how to graph quadratic functions by hand at this point. Right, so getting rid of these, put the function, now I'll just put y equals instead of f of x, y equals 3, for less typing, 3x squared plus x minus 2, right? And you see how it's, again, I don't care what happens here, but it goes up to the left, up to the right. The end behavior is what I described. Wonderful. All right, so the next one. Now, this one, it would be a huge pain, right? It would be a huge pain to multiply this all out, because you see it's 2 minus x to the 7th power. That's 2 minus x times 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 2 minus x, and what is that, 6? And then one more, times 2 minus x. Yikes, right? I'd multiply these two, and then multiply by this, then multiply by that result by this, and then multiply that result by this, and then multiply that result by this, and then by this. I mean, that would take a really long time. All right. So here's a little shortcut for you. The leading term of a polynomial function, if it's written out in factored form like this, right? This is a totally factored form. The leading term of this polynomial function is just the product of the leading term of each factor. The product of the lead term of each factor. Okay, so remember, the leading term is the highest powered term. So if you go through each factor, the leading term of each factor would be this negative x, right? That's x to the first power. 2 has x to the 0 power. So I'm just looking at the negative x's, right? The leading term of every single factor. So what we'd end up with for the leading term would just be negative x to the 7th. All right. Now the rest of it, I don't know. Okay, I mean, you could figure it out. Again, you can multiply this out, be my guest, write it in general form. We're not asked to write it in general form. Our only instruction is to determine the end behavior here. So the leading term of this polynomial, after all that multiplication, would be negative x to the 7th. Remember, negative 1 to the 7th would be negative 1. So the lead coefficient is negative 1, and then x to the 7th is, x to the 7th. So the leading term is negative x to the 7th, meaning that the lead coefficient is negative. Right, it's negative 1, so a negative lead coefficient. And the degree of this polynomial, again, is just the power on the variable in that leading term. So just 7, which is odd. That is an odd number. And this time, I'll get it right. Okay, I'll try to focus more. So a negative lead coefficient, odd power. So odd power, odd degree, negative lead coefficient. So like I mistook for the first example for up to the left, down to the right. All right, so the graph of this thing is going to go up to the left end, and down to the right end. All right, down on the right end. And if I'm describing this in symbols, say as x goes to infinity, right, the right end, the function is going down, and again this function is called f, so I'd say f of x is going to negative infinity. That's the right end behavior. And then the left end behavior, as x goes to negative infinity, right, going to the left end, the value of the function is going up, right, so f of x is going to positive infinity. And there you go, right, that's all they wanted from us, is describe the end behavior. Now let's actually verify it. I'll enter this function in my graphing calculator, right, that Desmos site. So again, instead of f of x, I'm just going y equals, and then we have the quantity 2 minus x to the 7th power. And look at that, right? See, up to the left, down to the right. It's got the same end behavior that I described after finding that leading term. Okay. So yeah, so to determine end behavior, you don't even need to know what the whole polynomial looks like, right? You just need to know what that leading term will be. And if it's in factored form like this, to find the leading term, you just simply multiply the leading term of every factor. It's really that easy. Okay. Next example. So I just got one more page. Now here we're asked for just a little different, right? Just a little different. We're asked to make a table to confirm the end behavior of the function. So I will describe the end behavior the way I have been. But then we'll look at a table and plug in higher and higher values of x in the positive direction and in the negative direction, and see that the outputs go the way I say they're going to go. Okay, so this example here, f of x equals negative x cubed, negative x cubed, it's the only term, so it's definitely the leading term. So the leading coefficient is -1, right? So negative. And the degree of this polynomial is 3, which is odd. So just like the last example, I have an odd degree polynomial with a negative lead coefficient. So the graph will do this, right? It'll go up to the left, down to the right. Again, we describe the end behavior. As x goes to infinity, as you go to the right, f of x is going down, right? F of x going to negative infinity. But as you go left, right, as x goes to negative infinity, the graph's going up, the output's going up. F of x is going to positive infinity. All right, so there's the description. Now let me make a table to show you that this is happening, to show you that as I increase the value of x, the value of f will get bigger negative, will go down, will decrease. And to show you that as I decrease the value of x, if I make x big and negative, the value of f will be big and positive. Get bigger and more positive. So I'll actually do that on the Desmos site with a table. Right? You can actually make tables here pretty easily. So our function is y equals, just negative x cubed, -1 times x to the third. And you can see the end behavior, right? It goes up to the left, down to the right. And if I go to settings here, or edit list, I can add a table. Right? Make a table for this function. Now what I'm going to do is I'm going to show you that the bigger values x, the bigger x gets, as x goes to infinity, the bigger negative y will get, the output will get. Right? So if I plug in 10, see it's -1,000. If I plug in 100, see it's -1 times 10 to the 9th, that'd be -1 billion. If I plug in 10,000, it's -1 trillion for the output. So you see the bigger 100,000, right? It's -1 quadrillion, right? So you see the bigger x gets, the bigger negative y gets, or f gets, the value of the function. So this shows me that as x approaches infinity, y approaches negative infinity. Right? Meaning as I go to the right, the graph goes down, which you're seeing in the graph here. Now if I just change all these to negatives, right? Well, let's just delete all this stuff. Right? We'll re-enter some values. Okay, so going back to the top here, Now what about the other way? What happens as x goes to negative infinity, as you go to the left? So what about like negative 10? You see the output's positive 1,000. And then negative 100. Go to the left even further. The output's positive 1,000,000. Even bigger positive. I plug in negative 1,000. Now it's 1,000,000,000. I plug in negative 10,000. It's a trillion, but positive, right? And again, you can keep doing this, but you see as I make x bigger and negative, right? As x goes to negative infinity, the output, right, the y coordinates are going to positive infinity. Exactly what I wrote on the paper. And this means as you go left, the graph goes up, right, what you're seeing in the graph here. All right, so let's clear that out, go back to my paper. All right. Okay, so that table, verified the statement I have in this box here about the end behavior. Or confirmed it. That's what they were asking us to do. All right, so example 6. Now again, you can multiply it all out, get it in general form, but all we're trying to do is identify the leading term. Now this is x squared times, and then 1 minus x squared is 1 minus x times 1 minus x. So if you take just the lead terms, multiply the lead terms, x squared is obviously the lead term of x squared, and then negative x is the lead term of 1 minus x, and negative x again is the lead term of 1 minus x. So the lead term for the whole polynomial is going to be x squared times negative x squared, right? Negative x times negative x. That's just going to be positive x to the fourth. Positive 1 x to the fourth. Now again, that's not the only term in the whole polynomial. If you multiplied all this out, you'd have x to the fourth plus a bunch of stuff. But I'm not trying to do that here. I'm just trying to identify the leading term. And once I have the leading term, the leading coefficient's easy. The leading coefficient is positive 1, right? So it's a positive number. And the degree is 4. Right? This is a degree 4 polynomial function, which is even. Right? So the graph of this thing with a positive lead coefficient and even degree is going to be going up to the left and up to the right. Again, if you want to describe that, that's, as x goes to infinity, the value of the function is going to infinity as well, right? The graph's going up. And as x goes to negative infinity, right, as you go left, the value of the function is also going up again, right, to positive infinity. So here's a description of the end behavior. And then they're asking us again to make a table, right, to confirm this. So I'm going to go back to the Desmos site and make a table for this, right, and show you that what I've boxed in here describing the end behavior is actually happening. All right, so the function we're given is, y equals, or f of x equals, x squared times the quantity 1 minus x squared, right? And look, see, up to the left, up to the right, exactly like I said. Now if I make this into a table, let's see. So see, if I plug in 10, output's 8100. If I plug in 100, see, the output is huge, 9.8 times 10 to the 7th. That'd be 98 million something. Right. If I plug in 1,000, right, now it's 9.98 times 10 to the 11th. That's even bigger. So you're seeing, as I increase x, as x goes to positive infinity, the output is also going to positive infinity, right? The output's getting larger and larger positive. And the same thing goes for negatives, right? If I just make all these negative, negative 10, negative 100, negative 1,000, you see the outputs are still big and positive, and they're getting bigger and more positive. So as x goes to negative infinity, as you go to the left, the graph's going up. All right, so this table does verify what I've stated about the end behavior on my paper, and you could see it in the graph there as well before it disappeared. All right, and then I got just one more example. This is it. All right, because again, it should be pretty simple, I feel, to identify the lead term. So this one's already written out in our nice general form. Now, if you don't like x to the 5th divided by 10, you can write that instead as 1/10 times x to the 5th, and then you got, minus x to the 4th, okay? But it's in that general form already, so the leading term is very easy to identify. It's just this, positive 1/10 times x to the 5th, the highest powered term. The leading coefficient is this positive 1/10, right, the number attached to the leading term. But it is a positive number, right? That's all I care about, if it's positive or negative. The degree is 5, right? That is an odd number. That is all I care about for the degree. Is it even or odd? All right, so positive lead coefficient, odd degree. So this will be the end behavior. The graph will be going down to the left and up to the right. And if we want to describe this, right, we would say, for the right end, as x goes to infinity, the graph's going up, right? The value of the function, f of x, is going to infinity as well, going up. And then for the left end, the graph's going down, so as x goes to negative infinity, right, as you move left, the value of the function is going to negative infinity also, right? It's going down. There's the description. Now I want to confirm this description with a table. Back to the Desmos site, I enter this function, y equals 1/10 times x to the 5th, then minus x to the 4th, and look, see, you can't see it there, but if you zoom out, it looked like it was going down on both ends, didn't it? But if you zoom out, you see it's going down to the left, up to the right, as I said. And then we put in a table, and again, let's just plug in, say 10. So you get an output of 0. Plug in 100. The output's what is that? 900 million. It got big quick. 1,000, huge. 9.9 times 10 to the 13th. 10,000, even bigger. 9.99 times 10 to the 18th. So you see, as x goes to infinity, as I move to the right, the graph's going up, right? The outputs are going to positive infinity. They're getting huge. Now the other way around, if I just make all these negative, negative 10, see the output's negative 20,000, negative 100, the output's negative 1.1 times 10 to the 9th. That'd be, about negative 1 billion. That's even lower. Negative 1,000, see, is even lower, even bigger negative. And then negative 10,000, it's even bigger negative, right? So what we're seeing from the table is that as I move left, as x goes to negative infinity, the output is going to negative infinity as well, right? Getting bigger and bigger negative as I move left. All right, so the table confirmed that, and again, you can see that in the graph once you zoomed out there. Great. All right, and that is all. All right, so again, hopefully this is easy enough. If you're given a polynomial function and asked to determine its end behavior, all you need to do is identify the leading term. And if it's in some crazy factored form, just multiply the lead term of each factor. That'll give you the lead term of the entire polynomial. And once you've identified the leading term, you then can identify the leading coefficient and the degree. All right, and with the leading coefficient, you just want to know if it's positive or negative. And with the degree, you just want to know if it's even or odd. And the leading coefficient and degree will tell you, what kind of end behavior the graph is going to have. Okay, so I'm hoping that watching me go through these 7 examples here help you in some way, when you're asked to identify the end behavior of a polynomial function on your own. All right, and thank you very much for watching.